They're just so weird. They just don't seem to do what you expect them to at all. Welcome back to the Home Lab, and today we're going to look at curves of constant width. What they are, their really interesting properties, and their connection to the Challenger space shuttle disaster. Once I've explained what they are and how they work, what we'll do is we'll build some and I'll demonstrate them in action, and I think you'll be surprised by their really unusual behaviour. But before we start, I just want to say a huge thank you again to PCBWay for encouraging me to make these videos. Apart from getting your 3D printing, CNC machining and bespoke printed circuit board manufacturer from them, do have a look at their website because they've got a brilliant shared projects section and you might get an idea from there for your next project. Curves of constant width are unusual shapes that have a constant distance between any two parallel lines touching their sides, and this gives them some really odd and interesting properties when they roll on a flat surface supporting another flat surface above. The most famous one of all is this one, the Rouleau triangle, named after a French mechanical engineer from the 19th century, Franz Rouleau, who designed this one, but you can make other examples with more than three sides. I first saw them set up as rollers like these here, Rotors, at a museum when I was a child, and I thought, gosh, those are really strange. So what I thought I'd do today is make a whole series of them and let's see how they behave when we roll them on a flat surface and support another flat surface on top of them, and I think you'll be surprised. I'd made one of these interesting shapes a while back from a couple of pieces of card and an old milk bottle that Barry had when he was a baby, but it wasn't very rigid, so I thought I could improve upon that. So I bought some different coloured sheets of 3mm plastic Perspex and downloaded from Wikipedia some interesting shapes that were all curves of constant width, not just three-sided ones. And I also have done a circle as well, just to compare that with these, and glued the shapes onto the Perspex sheets, and then I could cut them out on the bandsaw and make a whole series of rotors that I could demonstrate to you. By the way, if ever you find yourself wanting to draw parallel lines and be able to see through the ruler to what you're drawing underneath, I find using a mariner's parallel rule absolutely brilliant. And I also use these very fine long-tipped Pica pens, which I find brilliant for this sort of design work. So that each pair of curves was the same, I got each Perspex sheet and cut it in half first, and then sandwiched it together, and with the curve drawn on top of it, then cut it out on the bandsaw. So I ended up with two identical curves, and I did this for all of them, all in different colours. The colours don't mean anything, but I think they make it look just a little bit better. Sure, I could have done all of this with a 3D printer, but I actually like making things from scratch with my hands, and it's amazing what you can achieve with just a small tabletop bandsaw. It's also quite nice being outside in the garden rather than stuck indoors, and this time I was watched by our friendly blackbird that sits up on the roof and serenades us with song whilst I'm actually making my projects. Once I cut out the pairs of rotors, I then drilled a hole in them and countersunk that ready for an M5 bolt to go in. And I used some of this Perspex tubing here as an axle for each one. I then had to tap out the M3 threads in the axle to hold the bolts on either end. And something that might help you with this is if you've got an item that's quite difficult to hold on to, or you can't clamp in a vise very easily when you're working on it, I find stop it slipping, just holding it in your hand in some of that non-slip tabletop rubber matting works really, really well. Anyway, Barry took a real interest in what I was doing and immediately wanted to have a go at trying to see how the rollers worked on my flat workbench surface. One interesting property of these shapes is they don't have a fixed centre of rotation, and in fact the Rulu triangle is one of the worst of all. It might look like it does, but it doesn't in fact, which means that if you draw a line right the way across it and bisect it, and then draw another one and bisect that, the two bisection points, the two midpoints, don't sit in the same place, which means when you roll them on a flat surface, the axle actually moves up and down, or at least doesn't stay in the same place. The only one that would work for, of course, is a normal circle, and I've built one of those as well. So to demonstrate these working, what I had to do was build a frame that kept the rotors in place but allowed the axles to move around freely when these were rotating. So I built a frame out of some scraps of wood that I had lying around, and it's not really my best work, but you can see I've made some larger holes here, so when the rotors are rotating, the axles are free to move, but the rotors stay in the frame. You might also note that I've put the rotors in order of number of sides. So I've got 3 here, 5 there, 5 there, I think that's 7, and I think that's 9. I know the mathematicians amongst you will say, well, what's the circle doing at this end? I just wanted to put it at that end. You can imagine it having one side, but of course it's the opposite of that. It should be at this end, having a sort of infinite number of sides to make the circle. But it did help support the thing quite well. So the next thing we need to do is actually have a look at it working. So the time came to try it out on the workbench, and I put a sheet of wood on top, flat sheet of wood, and some bricks, and rolled it along the desk, and it worked reasonably well, but I found that the 3-sided Rulu triangle one didn't. It just sort of slid along the desk. I thought I'd made the circular one a little bit too large, and that was the problem. So I filed it down a tiny bit, and then I suddenly realised, of course, that there wasn't quite enough friction between the perspex and the desk. So the solution was staring me in the face. Put that rubber non-slip matting down again, and when I put that on the desk and slid it up and down, it worked perfectly. So here you can see the really counterintuitive nature of these curves of constant width. That in fact, remember the parallel line test, that if you've got a flat surface and a flat surface above them, they will remain at a constant distance apart. So when you roll it up and down, even though the centre of rotation of each of the little rotors changes, the distance across them doesn't, so they'll keep the surface above completely level, and it won't bounce up and down like you think it might have done. Yes, I can hear you say it again. Get a 3D printer, FJ. But I always say, I find that if you make things from scratch, you can make little changes as you go along, which I did with these, rather than being stuck with an artifact that's already made. I also feel that you get kind of closer connected to the project as you make it bit by bit. And that in the end seems to give you a much better understanding of the object you've made. Oh, just to add that if I did have a 3D printer, I think once I've made things by hand and sort of got bits right and got bits wrong and modified my design, then my final example would be so much better if I actually printed the whole thing. But this is rather large, so maybe I would need a very large 3D printer. So, in summary, have a look around you for these interesting shapes, and you might see them pop up more often than you think. The Rulu triangle actually is used quite a lot in church windows and for sort of emblems on buildings as well. And there's a really weird and interesting example on the Mount Zion Primitive Methodist Church in Madeley, near where I am. They're also used in the UK for the 50 pence and the 20 pence coin. Because they've got a constant width across them, it allows the coin mechanism to easily measure them and check they are genuine coins. Now, it's worth pointing out again that these are curves of constant width, not constant diameter. And that problem became disastrously apparent in the Challenger space shuttle disaster. Very quickly, to explain it, the solid rocket boosters on the side of the space shuttle were made of sections that were linked together. And once those were used, they were jettisoned and they came down on parachutes and landed in the ocean and were reused, which was a good saving of material and cost. What they needed to do before they joined the sections back together again was to check that they were circular. So what's the obvious thing to do? Well, measure the diameter, measure the diameter, measure the diameter, measure the diameter, and clearly they were circular. But of course they weren't. They'd been damaged and twisted and bent slightly, so in fact they had a constant width. And when mated back together again, also with slight problems with the O-rings, you can imagine you were putting shapes together that weren't quite circular, which gave slightly bigger gaps in some places than in others. Well, it took the genius of Richard Feynman to think this one through, and the story that he tells is really interesting. But just like me, he remembers seeing these really weird rotors when he was a young boy, and he thought, I wonder if that's the problem they had with the solid rocket boosters. So I do hope you enjoyed that video on curves of constant width, and you can see how I took a simple design in the early stages with the baby milk bottle and the bits of card and turned it into an artifact like this, which demonstrates how these things work really well. Anyway, do stay to the end of the video because as you remember, I often cut in bits of film that you haven't seen, and right at the end I put some links to some other videos that might interest you. So I hope to be making another video soon, and please do join me then.